Up to this point, we've derived our coordinate descent algorithm for least squares, and we've discussed what the variant is for lasso, but we didn't derive explicitly why our coordinate descent algorithm for lasso has that soft thresholding form. And for completeness, we're going to include the derivation, but as an optional video. And I really want to emphasize that this video is optional. The material is quite advanced. It's actually material that's typically taught at the level of a PhD or grad level course. So watch it at your own risk. We think it's still very interesting if you want to see what's under the hood in the lasso solver. But that's our little word of warning before we delve into this content, because again, this is an example where the level of what we're going to present in this video goes much more technical than what we're assuming for the rest of this specialization. Okay, so let's get into optimizing our lasso objective, which we've written here. And we're doing it again, one coordinate at a time to derive our coordinate descent algorithm. And in this derivation, we're going to use unnormalized features. So we're not doing the normalization. This is just our typical H that's appearing here. And we're doing that because that's the most general case we can derive, and the normalized case follows directly from this derivation. Okay, so to start with, let's look at the partial of our residual sum of squares term with respect to Wj. And we did this derivation when we were looking at deriving coordinate descent for least squares, but we did it for normalized features. So let's do it now for unnormalized features, where remember what we're going to do is just pull out this Wj term. So we're going to get sum I equals 1 to n hj of xi, and I'm going to skip a step assuming that you remember what we did on that previous video where I'm separating out the sum k not equal to j, wk hk xi, from this term where we get the wj hj of xi. And so when we do this multiplication, we're going to get minus 2 sum over I equals 1 to n hj xi times yi minus sum k not equal to j wk hk xi. And here we're going to get plus 2. Again, the wj comes out. We get sum I equals 1 to n and hj xi squared. And when we were talking about normalized features, we said the sum of the hj squared was equal to 1. But now we're looking at unnormalized features. So let's define some terms. Again, we're going to call this term, even though in this case we're looking at unnormalized features, we're still going to call this rho j. And here, now we have to define what we're calling this normalizer, and we're going to call this zi. I mean, sorry, not zi, zj. Okay. So the result, oops. If I go back to my blue colors, we get minus 2 rho j just like before, but now we get plus 2 wj zj. So that completes our residual sum of squares term. Now let's turn to our L1 penalty. And this is where things become more complicated. So in particular, what's the partial with respect to the absolute value of wj? Remember, that's all the other terms we're thinking of as held fixed. So we're just looking at this wj component. Well, this is where we get these derivatives of absolute values that become problematic. Remember, here we have derivative is equal to minus 1, and here we have derivative equals plus 1, and here we have this problem point. And we mentioned that instead of thinking about gradients or these partials, we think about subgradients. Okay, so now let's talk about these subgradients and formalize this a bit. But let's first mention that gradients we can think of as lower bounding convex functions. So if I look at my convex function at some points A and B, if I take the gradient at my point A, that's this tangent plane. So this is gradient of G at A. Then what I have is I have that G at B. So just to be clear, this is G of A, G of B. So G of B is greater than or equal to G of A plus gradient of G of A times B minus A. And importantly, gradients are unique at x if the function is differentiable at x. Well, subgradients generalize this idea of gradients to non-differentiable points, and a gradient is going to be any plane that lower bounds this function. So, sorry, not a gradient. If I said a gradient, I mean a subgradient. So a subgradient is really a set. It's a set of all the planes that lower bound a function. So we're going to say that V is in our set, which we denote by this curly D of G at a point X. So this is our subgradient of G at X if we have that G of B is greater than or equal to G of A plus, in place of this gradient here, we're writing V. So here this was the one function that lower bounded our, the one plane that lower bounded our function. And here this is one of the planes that lower bounds our function. And again, we have B minus A. So this is the definition of a subgradient. And let's look at it in the context of this absolute value function. So what are all planes that lower bound this absolute value function? Well, all the planes that I'm going to draw lower bound this absolute value function. There's this plane, there's this plane, there's this plane with positive slope, and I could fill this space here with all these planes. And what are the slopes of these planes? So here we know that the slope is equal to -1, and here the slope is equal to +1. And we see that anything that has a slope in the range of -1 to 1, any line in the range -1 to 1 is going to lower bound this absolute value function. So for the absolute value of x, we have that v is in -1 to 1. So -1 to 1 represents our subgradient of the absolute value of x. So now that we've had our detour into the world of subgradients, we can start talking, instead of the partial of this L1 term, we can talk about the subgradient of this L1 term, where here we get lambda times the subgradient. We already know the subgradient of the absolute value is the range -1 to 1. So lambda times the subgradient of the absolute value is going to be minus lambda to lambda when wj is equal to 0. And remember that subgradient is defined at that problem point, wj equals 0. But in the case where the derivative exists, or that partial exists, it's just going to be lambda times, in the case of w less than 0, we had -1. So this is lambda times -1. Here we have lambda times minus 1 to 1. In the case where we're in this positive half plane, we get lambda times 1. Okay, so this is our complete lambda times the subgradient of our L1 objective with respect to Wj. And now that we have the partial of our residual sum of squares term and the subgradient of our L1 term, we can put it all together and get our subgradient of our entire lasso cost with respect to Wj. And here, this part, this is from our residual sum of squares, whereas this part is from the L1 penalty, or really lambda times the L1 penalty. And when we put these things together, we get 3 different cases because of the 3 cases for the L1 objective. So we get 2 Zj, that normalizer, Wj minus rho j minus lambda. I won't read all of the different cases, but this now is our subgradient of our entire lasso solution. Okay, well, let's not get lost in the weeds here. Let's pop up a level and say, remember before we would take the gradient and set it equal to 0, or in the coordinate descent algorithm, we talked about taking the partial with respect to one coordinate and then setting that equal to 0 to get the update for that dimension. Well, here, now instead of this partial derivative, we're taking this subgradient and we have to set it equal to 0 to get the update for this specific jth coordinate. So let's do that. So we've taken our subgradient, we're setting it equal to 0. Again, we have 3 different cases we need to consider. So in case 1, where Wj is less than 0, let's solve for W hat j. We get W hat j equals 2 rho j plus lambda divided by 2 zj, which I'm just going to rewrite as rho j plus lambda over 2 divided by zj. So I've multiplied the top and bottom by 1/2 here. Okay, but to be in this case, to have W hat j less than 0, we need a constraint on rho j. So if rho j is less than minus lambda over 2, remember this is that correlation term, if that, and that's something we can compute because that's a function of all the other variables except for Wj. So if rho j is less than minus lambda over 2, then we know that W hat j will be less than 0 according to this formula. Okay, then we get to the second case, which is Wj equals 0. In that case, we've already solved for W hat j. There's only one solution. But in order to have that be the optimum, we know that this subgradient, when Wj equals 0, the subgradient has to contain 0. Otherwise, we would never get that this is the case that is equal to 0, that it's an optimum. So we need for this range to contain 0 so that W hat j equals 0 is an optimum of our objective. And for that to be true, we need minus 2 rho j plus lambda to be greater than 0. So we need this upper term of the interval greater than 0, which is equivalent to saying that rho j is less than lambda over 2. And we need this bottom interval to be less than 0. So minus 2 rho j minus lambda less than 0, which is equivalent to saying rho j is greater than minus lambda over 2. And if we put these together, what this is saying is that rho j is less than lambda over 2 and greater than minus lambda over 2. And actually, we could put the equal sign here. So let's just do it. So it has to be less than or equal to, less than or equal to, less than or equal to. Okay. In our final case, let's just quickly work through it. We get W hat J equals rho J minus lambda over 2 divided by Zj. And in order to have W hat J be greater than 0, we need rho J to be greater than lambda over 2. So let me just talk through this kind of in the other direction now that we've done the derivation, which is saying if rho J is less than minus lambda over 2, then we'll set W hat J as follows. If rho J is in this interval, we'll set W hat J equal to 0. And if rho J is greater than lambda over 2, we're going to set W hat J as this third case. Okay, so this slide just summarizes what I just said. So this is our optimal 1D optimization for this lasso objective. So let's talk about this more general form of the soft thresholding rule for lasso in the case of our unnormalized features. So remember, for our normalized features, there wasn't this Zj here. And what we ended up with for our our least square solution when lambda was equal to 0 was just this line W hat J equals rho J. But now what does our least squares line look like? Well, again, we can just set lambda equal to 0. And we see that this least squares line, W hat least squares, is equal to rho J over Zj. Remember, Zj is that normalizer summing over the square of all of our features. So that number will be positive, and it's typically going to be larger than 1, potentially much larger than 1. So relative to a slope, just a 45-degree angle, a slope of 1, I'm saying that this line is shrunk more this way, typically, in the case of unnormalized features. And then when I look at my lasso solution, W hat lasso in this case, again in the range minus lambda over 2, sorry, that is clearly not minus lambda over 2. This is minus lambda over 2 to lambda over 2. I get this thresholding of the coefficients exactly to 0 relative to my least square solution. And outside that range, the difference between the least square solution and my lasso solution is that my coefficients are each shrunk by an amount lambda over 2zj. Okay, but remember that rho j here, as compared to when we talked about normalized features, was defined differently. It was defined in terms of our unnormalized features. So for the same value of lambda that you'd use with normalized features, you're getting a different relationship here, a different range where things are set to 0. So in summary, we've derived this coordinate descent algorithm for lasso in the case of unnormalized features. And in particular, the key insight we had was instead of just taking the partial of our objective with respect to Wj, we had to take the subgradient of our objective with respect to Wj. And that's what leads to these 3 different cases, because the gradient itself is defined for every value of Wj except for this one critical point, Wj equals 0. But in particular, we also had a lot of insight into how this soft thresholding gives us this sparsity in our lasso solutions.